We are finally about to begin proving the fundamental theorem of calculus. This is only part 1 of that theorem. It's only the first of 3 videos, but we are about to begin. So let's start with what we already know. Excuse me. We already know the definition of a definite integral. The definite integral is a sum. And it's not just any old sum, it's an infinite sum of infinitely skinny little rectangles. So let's go over everything we know about it. We have a definite integral that goes from a to b of a function f of x. And we divide that space from a to b into n rectangles. We call each space delta x, b minus a over n. And we sum up the area of each rectangle. But in order for this to be an integral, we have to think about the limit of this sum as the delta x goes to 0 and the n goes to infinity. Those are companion ideas. When n goes to infinity, delta x goes to 0. So the only other thing we're making clear here, which we haven't looked at closely before, is all the little x values that divide the interval from a to b into the little infinite n spaces. So we say a is the first one, x sub 0, and b is the last one, x sub n, and we just number them with subscripts. X sub 0 to x sub 1 is the first delta x. X sub 1 to x sub 2 is the second. And as delta x goes to 0, these get closer to each other, and n gets larger and larger. And we have an infinite set, and we know how to name them. So this is what we know about a definite integral, and this is what we want to prove about it. We want to prove this idea that we have been building evidence for, that the definite integral from a to b of f of x dx is the difference between the antiderivative at b and the antiderivative at a. A to b is a closed interval, and f of x is continuous on that interval. We haven't dealt with any integrals where there's a discontinuity. And the derivative of capital F is f. If we have that relationship, then capital F is considered the antiderivative of f. We want to prove this. The way we start that proof is by looking at the mean value theorem. The mean value theorem is actually a very simple and easy to demonstrate theorem. Here we're looking at mean, referring to average. Average is referring to average change or slope. So the mean value theorem says if you have a function, y equals f of x, and it's a function on this closed interval from x equals a to x equals b, and we connect the points of the endpoints of that interval, so we get a line segment with a slope. By the way, that slope represents average change from x equals a to x equals b on this function. Well, we're always going to be able to find a point C, where the derivative at C, the slope of the tangent, is the same as the average change, the slope of this line segment. So let me try to say that again. We connect the endpoints on this interval. This is the point A, f of a. This is the point B, f of b. So we have a line segment with a slope. There's a point C where the derivative at C equals that slope. Now, whether you think that's remarkable or not, the best way to understand it is to actually do it, to try it. So we're going to start with a particular function. It's a cubic. You can see that because it has 3 intercepts. It's y equals x cubed minus 3x squared plus 20x plus 100. And we're going to look, I've selected the interval from a to b. A is 0, and the function at 0 is 100. And b is 5, and the function at 5 is 0. And if you connect these points, you can see the slope of the line is negative. And if we use the 2 points, 0, 100, and 5, 0, we can calculate the slope. 0 minus 100 divided by 5 minus 0 is a negative 20, which seems right. This is a sharply sloped, negative sloped segment. So the mean value theorem says, well, if we take the derivative, here it is, 3x squared minus 26x plus 20, we should be able to find a c somewhere in here, somewhere between 0 and 5, where this derivative at c will be negative 20. Well, let's do it. Let's say that negative 20 equals the derivative, and let's solve for x. Well, I added 20 to both sides, and I get a quadratic equaling 0, so I can use my quadratic formula. 0 equals 3x squared minus 26x plus 40, because I added 20 to both sides. So negative b is negative 1 times negative 26, or positive 26. And we're going to add or subtract b squared minus 4ac. 3 is a, 40 is c. And negative 26 squared is the same as 26 squared, so that's why I use 26 squared here. The nice thing about this discriminant, this b squared minus 4ac, is that it's 196. And the square root of 196 is 14. So we get the much simpler expression, 26 plus 14 over 6, or 26 minus 14 over 6. If we add 14, we get a number that's not between 0 and 5. 20 divided by 3 is bigger than 6. So that won't be in here. We don't even have to look at it. But if we subtract 14, we get 12 over 6, and that's 2. At x equals 2, that's going to be our c value. The derivative is negative 20. And I graphed it for you so you could see how it actually looks. Here's our cubic. Here's our average change from x equals 0 to x equals 5. And with a vertical line at x equals 2, and you can see the slope of the tangent at that point is the same as the slope of the line connecting the endpoints, connecting 0, 100, and 5, 0. Let's look at another example. And let's think about whether there's only one value of c or maybe more. So here we don't have the equation. We have to do it visually. We're going from x equals a to x equals b on this green function that goes up and down. And one point has been shown here where it looks like the slope of the tangent, the derivative at c, is the same as the slope of this average change line. But if we follow along this function, it looks like maybe over here we have a similar value. We have another value where, let's see if I can draw it nicely. Well, mine's a wiggly line, but clearly somewhere over here the slopes are going to be the same. And as we come around, somewhere over here, oh, that's so terribly wiggly. Try one more time. But I want to make this point that however poorly I drew this line, it's not that there's only one point C where the slope is the same as this average change. There can be many if the function goes up and down. Let's look at another example where we have the equation. So this is y equals 2 sine of 1/2 x. It has the shape that you expect from the sine function. And I picked an interval between pi and 3 pi. Those are the x values. Pi to 3 pi, and the y values are 2 to negative 2. And we connect these 2 points, and we get a sharply negative slope. But notice as we travel around this function, somewhere over here it looks like we have a point where perhaps we'll have the same slope as the average change. And then as we come around the tangent, we have another point over here. So again, C is not unique, but there always exists a C. There always exists one point where the slope of the tangent at that point, the derivative at that point, is going to give you the same value as the average change on the whole interval. Now you may say to yourself at this point, why do I care about this? What's the point? Here's a statement of the mean value theorem, and it seems maybe okay, true, but not remarkable. But notice something. This mean value theorem connects a function and its antiderivative. Here's a function, f prime, and its antiderivative, f. And that's part of the challenge in proving the fundamental theorem, connecting a function to its antiderivative. Connecting a function to its antiderivative. Connecting the function to its antiderivative. So you're going to have to practice the mean value theorem, make sure you know that it's true, because it's going to be essential to proving the fundamental theorem of calculus.